Okay, so with the three simultaneous equations, there is a massive connection with geometry of planes, so three-dimensional planes, and their intersections with each other. I need to be able to recognize by inspecting the solutions or determinants whether those, what kind of solutions you're going to get, if any. Now, if there is a solution to your system of simultaneous equations, then those equations are called consistent. Okay, if there isn't a solution, they're called inconsistent. Okay, so if you have got three equations, they will be consistent always if you can find the determinant of the matrix that's associated with this system. So here, look at the coefficients of x, y, z in each equation. Here, these are written here as entries to the matrix. If you can find the inverse of that matrix, it's going to be consistent. And then there is one solution, one unique solution. If you are going to connect this to geometry, each of those equations represents, it's got three variables, 3 dimensions, represents a plane. We'll talk about planes in another chapter. I think it might be next chapter. That means those 3 planes will meet at one point. So it will look like this. Probably going to be rubbish at drawing it, but let's just give it a good try. Like that, maybe. There's another plane. So that's 2 planes, they are connecting a point, and if I add another plane, maybe sideways like this. See, those will meet at one point over here, okay? Now, if they are inconsistent, so there is no inverse matrix, it gets a little bit more complicated, because it doesn't mean that you can't solve them. There might be still solutions, okay? There won't be one solution, but you could have consistent equations. That means you can have infinite solutions, okay? Let's start. So this is when a matrix associated is singular. You will have infinite number of solutions. You can have situations where you've got all of those equations actually represent the same plane. So that's just easy. Somebody multiplied one equation by different constant with different number, and you actually all of them can be reduced down to the same. They are the same equation. That simply means that they are just going to go be on top of each other. Okay, that's just one equation. Infinite number of solutions, all the points on that plane. You could also have consistency, where you've got the planes that form sheaf. I'll talk to you about it in a second. This is a sheaf, which is geometrical representation. Now, how do you do that? So you're going to find out that that is equal to 0, and then you're going to attempt to solve that. So you're going to solve it not like we've done the previous example, but by eliminating one of the variables. Go normally for z. So the way you're going to do it, you're going to just do simultaneously, make sure that you do the elimination method, so have the same number of z's from the first 2 equations, and you end up with 2 equations in terms of x and y. And then you're going to do the same for the other set, so maybe equation 2 and 3, do exactly the same. You end up with 2 equations in terms of x and y. Okay, now the same, if the same equations, you get the 2 of the same equations from both applications, so considering the first and second equation and second and third, that means it will form a sheaf, because it represents a straight line, 2 variables, straight line. They could be multiples of each other, but they can be reduced down to the same straight line. They form a sheaf. So that means the planes intersect at a straight one line. So let me just again attempt to draw it. So let's have one plane maybe like this, another maybe like this, and then might be one like that. There you go, and they all intersect, a little bit of wonky there, at one plane. So there you go. So these are the two situations where you can have consistency, and the matrix and the determinant of the matrix is equal to 0, so there is no inverse. Okay, again, there's infinite number of solutions for this one. Now, they can be inconsistent. Again, you need to know what happens because it's two different situations. So that means inconsistent, no solutions. So you are going to have the same go as with the sheaf. So you found the det is equal to 0. You are going to eliminate the third variable from two pairs of different equations. So maybe 1 and 2 and 2 and 3. And you end up with two equations with two variables, so maybe x and y if you've used that method. Now, if they are different and the two they have no solutions. So I'll give you an example what not solutions. For example, you might be left with 2x plus y equals 7 is one of the equations, and maybe 2x plus y equals to 1. That is impossible. You can't solve this. Yeah, so those three planes will form what's called a prism. Okay, so that's what it would look like. Let me just imagine. So you've got one plane like this, one plane like this, and then maybe have another one like this. There you go. Okay, so they meet each other. Two planes will meet each other, but they form a prism. It's not a very good drawing, but have a look in the book if you want a better representation of that. Okay, and finally, if you've got the three equations, those here, and you can see clearly the first two maybe are exactly the same, so they're multiples of each other, and you've got a third one that's totally different, then you know that they are inconsistent, because what it tells you that actually, let me just say, they can be not exactly the same as each other. They need to have the left hand side the same, so like this. Okay, so let me just give you an example. You could have 2x plus y plus z equals 1, and then 2x plus y plus z equals 5. See, those equations here, they are exactly the same on the left hand side but different on the right hand side. And then maybe you have a third one, x plus 7y minus z equals 4. Now, if you see this one here, that tells me that these two will be parallel to each other, and this one is not going to be parallel to both of these. So if they are parallel to each other, you can't solve them. If you try to eliminate z from this one, you will end up with 0 equals to minus 4, which is rubbish. So in this case, you will have two planes that are parallel to each other, and then one that intersects them, like so. There you go. There you go. Okay, so let's have a go at example 22. So what they're asking us to do is just to have a look at this system of equation. You can see that some numbers have been replaced with letters. And depending what the letter is equal to, we are going to find out whether there is a solution or no solution. And I think in case where there is a unique solution, oh no, we don't need to find out, but we need to identify geometric representation. So if I make k equals 0, let me just write this as a matrix. You will have 3, 0, minus 6, 0, 3, 3, and minus 3, minus 1, 3. So the first step should always be to find det of this one. So you're going to take this entry, so 3, and then do the det of the remaining numbers. Matrix minus 0, okay, I don't need to do the det, minus 6 times what's remaining, 0, 3, minus 3, minus 1. I didn't need to write the matrix here because it's 0 times something is 0, but actually for just so you're consistent, let's put it in, it'll be 0, minus 3, 3, 3. Okay, so it's going to be 3 times 9 plus 3, so 12. And here we're going to do minus 6 times 0 plus 9, so times 9. So it's going to be 3 times 12, which is 36, minus 54, which is minus 18. Okay, so that means there is a unique solution. 3 planes intersect at one point. That's geometrical representation. So they intersect or meet at one point. Let's put 1 instead of 0. So we are going to get 3 minus 1 minus 6, 1, 3, 3, minus 3, minus 1, 3. So let's find det of that one. So it's going to be 3, and then 3, 3 minus 1, 3, plus 1, because that minus 1 changes to plus, 1, 3, minus 3, 3, and then minus 6, 1, 3, minus 3, minus 1. Okay, so you got 3 times 9, so that was 12. This is 3 plus, so that's plus 12, minus, and that one is going to be 6 times minus 1 times, minus 1, minus minus 9, so plus 8. Okay, so that's going to be 48, because 36 at 12 minus 48. So that is equal to 0. So what that tells me, it could be consistent and intersect at a one line, which forms a sheaf, or it could be the same plane, but clearly it's not, because none of these represent the same combination of x, y, z, and you need to consider what's on the right hand side also. So we need to now attempt to eliminate, well, we need to make a start at solving. So do what you would do if you were to solve it without using the inverses. So that's the first equation. The second equation is x plus 3y plus 3z, forgot the z here, is equal to 2 minus 3x minus y plus 3z is equal to minus 2. That doesn't change if I've done that one right. I think that's correct. Good. Okay, so we're going to eliminate, let's call that equation 1, equation 2, equation 3, so you know exactly what I'm going to do. So, all right, let's eliminate z. So I'm going to add equation 1, and if I multiply that by 2, 2 lots of equation 2 together. So let me just write down what it looks like for this purpose. If you add them together, you're going to get, let's put it down, that's going to be 5x plus 5y is equal to 5. So it's x plus y is equal to 1. And then we're going to do the second equation, eliminating z. So let's take the second equation and subtract this time the third equation. So I don't need to rewrite it. So that take away that is going to be 4x. 3y take away negative y is 4y. And then 2 take away negative 2 is 4. So that is also x plus y is equal to 1. So they are the same, but I consider two different equations, eliminating z. So they are, let's put it to everything, they are consistent and infinite number of solutions. The planes intersect at or along a straight line, and they form sheath. Now you can actually spell it with TH, but I marked the paper a couple of years ago. If people, some spelled it as, with double E, and they lost that mark. So you need to mention sheath, spell it correctly. Say also that they intersect at a straight line, there's infinite number of solutions, but also look. So I want to see this written down, I want to see that they are consistent, and geometrically say that they form a sheath. Okay, so let's just look at the last one, which I don't think I've got enough room on this piece of paper. I'll just do this one here. So what happens if I make k equal to -6? So if k is equal to -6, I'm going to get 3, and then that will become -6, so plus 6 minus 6. I'm going to find that of that. And -6, 3, and 3, and they've got -3, -1, 3. Okay, so what is the det? 3, and then 3, 3 minus 1, 3, -6, -6, -3, 3, 3, and then -6. Okay, so that is equal to 0. We're going to just do the elimination again. Equal to 2. Again, label that 1, 2, 3 maybe, or A, B, C. Okay, so again we'll double that, and we are going to add 1 to 2 lots of 2. So what will I get? I'll get 3x, and if I double that is -12. So it's going to be 3 minus 12 minus 9x, then 6 add 6, which is 12y, and then on this side -6 add 4, which is -2. And then for the second lot, so we'll do taking away, so we'll do 2 minus 3. So we have got -6, take away -3x, that will give you -3x. 3y, take away y, so that's 4y. And at the end I will have 2, take away -2, so it's add 2, which is 4. Okay, so over here what we notice now, if you try to solve these, you won't have any solutions. Okay, I'll divide this one, no, multiply this one by 3. So you will get -9x plus 12y is equal to -2. And then if you multiply this one by 3, you will have, just to attempt to solve it, -9x plus 12y is equal to 12. So you could see that if I take one away from each other, so it cannot be solved. So inconsistent, and because you end up with like 2 different equations, let me just show you, oh, it's on the other side of it. the equations that are exactly the same but different numbers on there, they represent parallel lines, but they form a prism. There you go. The planes form a prism. So now you can go and do exercise 6.